So next we need to talk about the variation or spread of our data. It's one thing to find the middle or center of our data and to know about the distribution, but then understanding how the variation or spread of our data brings all that together is really important. So two major things we use for this spread is the standard deviation and the variance. And essentially we calculate the variance first and the standard deviation comes from that calculation. The one we'll use most this semester would be the standard deviation. In a second semester statistics class, you talk more about the variance, but we won't really get into that this semester. So one thing we need to do is to talk about how to calculate these things, but the most important thing to get from the idea of standard deviation is what it tells us about the data set. Okay, what does the standard deviation mean, and what does it tell us about the data set? How can we use it? Yes, you have to do the calculation properly, but you need to be able to look at the calculation of the standard deviation and understand what it means. So let's start with that, and then we'll get into the calculation, which is probably the most difficult calculation we're going to have the entire semester. Right? So it's going to take us a little bit of time to get good at it. So here's a list of ages of Jasmine's close friends. And we look at these 10 different ages here. Okay, we could find the mean, the average age. And the average age is 41.5. Okay, so every friend is either older than that or younger than that, right? So every friend essentially deviates from that average age, from that mean age. Okay. Now, one question that we're going to ask is there a number we can calculate that will measure how much the overall deviation of all these ages is from this mean? And the answer is yes, that's what the standard deviation will give us. So let's think about this a little bit. We know the mean is 41.5. So if we looked at all these ages and we made a little table and listed all the ages down this first column, we could calculate the deviation of each age from that mean. And when I mean deviation, I mean difference. Okay? How far away from the mean is each of these ages? So I could do that simply by subtracting. So 41 minus the mean, 41.5, is minus 0.5. Okay? 38 minus 41.5 is minus 3.5. And again, that's telling us each individual data value's deviation, how much it varies from the mean. Notice when we get a negative answer, it's because these data values that are giving us these negative deviations are below the mean. And when we get a positive deviation, these are above the mean. Okay, they're bigger than the mean. So we can look at all these individual deviations. But what we want to know is how does the data set overall deviate from the mean? So you can look at all these, and one thing we could do is to say, okay, well, let's add all these deviations up. Okay, the individual deviations, let's add all the individual deviations up. Problem here is that's always going to end up being 0. Always. Okay, when you look at any data set and you look at the deviation overall of every data value from the mean and sum them all up. So we take the sum of the deviations of each data value from the mean, which is the difference of the data values and the means, you're going to get 0, okay? Which is not super helpful. So we need to do something to kind of account for that so that we can calculate the overall deviation. So two things we could do. One is we could square each of those deviations, therefore then make them all positive and work with that. Or we could take the absolute value of all of them. That would also make them all positive. What we're going to do is we're going to square them. Okay? So if we took each of the individual deviations for each data value, and that's what these values are right here, okay? And we square each one, now we have the square of all the different deviations, and we have them listed here. What we'll do is we'll add all of those up, okay? So we'll add up the square of all the deviations, in which case what we're going to get is 88.5. Then after we do that, what we're going to do is we're going to divide by the total number of data values in this population. And this is a population, this is not a sample, because this is the set of all of Jasmine's friends. Okay, it's the total group. Remember, population is the total larger group. If we just look at it like 3 of her friends, that would be a sample, but this is all of her friends. She's got 10 friends. And so what we'll do is then we'll divide by the total number of data values there after we sum up the square of all those deviations. And what we're going to get is this number, 8.85. That number right there is what we're going to call the variance. Okay? That is the variance of the ages. Okay? Now, what that variance is the measure of the square ages of all of her friends. Okay? It's the square ages, but that's not really going to make a whole lot of sense here. We only squared all those deviations so that they were all positive. So really what we want to do is eventually get rid of that square, right? We want to make some sense of this actual thing that we're calculating of the deviations, the overall deviations. So what we really want to do is not look at the overall measure of the square ages of all of her friends, but we want to look at the overall deviation of ages. So to remedy that square thing we did earlier in the calculation, we'll take now the square root of the variance. Okay, so this is how we calculated the variance. We're going to take the square root of that to kind of remedy the square we did, and the square root of 8.85 is 2.97. And that 2.97 is what we're going to call the standard deviation. Okay, that is the standard deviation. So now what does that mean? It means that these 10 friends had an average age, a mean age of 41.5. Not every friend was 41.5. In fact, none of them were. Some were below 41.5, some were bigger than 41.5 in terms of their age. So they all deviated. The overall deviation of the data set, the amount that the data set's varying away from the mean, is at a rate of 2.97 years from that 41.5. So these data values here, these ages, are all varying away from the mean at a rate of 2.97 years from the mean of 41.5. Now, when we just did that problem, we were working with a population. It was a population of all of the friends. Okay, the 10 friends was all of the friends. When we're working with a standard deviation of a population, we use this symbol right here. This is a sigma symbol as well. It's a capital sigma symbol, but all you need to know is it's the standard deviation of the population. And this was the formula we just did. If we were going to try and find the standard deviation of a sample, we really do it largely the same way. There's one slight difference. We use lowercase s as the symbol. Right? We have 2 different symbols because we're going to compare samples and populations. Notice the mean, we had x bar and we had mu for sample and population. And for standard deviation, we have 2 different symbols as well. And the formula, if you look at it, looks very similar. There's one major difference, and the major difference sits right here. And in that, when we divide, we don't divide by the total number of data values. We divide by the total number of data values minus 1, okay? And so it's n minus 1 instead of just n. Now, there's a reason for that, but there is a difference in the formulas. Other than that, it's really the same thing. This is the deviation of each data value from the mean, just using x bar instead of mu. We square those deviations, we add them all up, we divide by n minus 1. That calculation inside the square root, that's your variance. And then the square root is to undo the square, and that's going to be our standard deviation. But we divide by n minus 1 in a sample. Now, the main reason why we divide by n minus 1 instead of n for the sample standard deviation, it really has to do with actually the sample variance. Okay? What we always want to do is we want to use our sample values to estimate our population values. And we want our sample values to really reflect what's happening in the population. And when it comes to variance, the calculation we do before the square root, okay? If we were just to divide by a lowercase n instead of an n minus 1 for the sample variance, it actually doesn't give us as good of an estimate of the population variance as dividing by n minus 1 does. So, it's some real kind of heavy theoretical math inside there, but that's the main reason, is that it has been seen that the sample variance will be a much better reflection of the population variance if we divide by n minus 1 than if we divide by n when it comes to the sample variance. Okay? Population doesn't really make a difference, because in population, that n is typically a really big number. And if it's a really big number, subtracting 1 off of it doesn't really make much of a difference. Whereas in a sample, lowercase n is a relatively small number. Okay? And subtracting 1 off of it does, affect the calculation. Okay, so if we thought of this more of a sample than a population, so let's change the question a little bit. Let's say Jasmine doesn't have 10 friends total. She has 1,000 social media friends. And out of those social media friends, thousands of them, we look at 10 of their ages. So now we're talking about a sample of her friends. So the same data set we were talking about before is actually now a sample instead of a population. And we want to calculate the sample variance and the sample standard deviation. Well, we do everything the same way. It's the same data set, except for once we get to the sum of all the deviations squared, which was 88.5 before, we're now going to divide by n minus 1 instead of n. And that's going to be divided by 9. And so we're going to get 9.83 as the sample variance. Okay? Remember, that value before we hit the square root, that's your variance. Then we'll take the square root of that, and take the square root of this, and we're going to get the standard deviation. Again, doing it this way by n minus 1 instead of n, we're actually going to get a better estimate than we would have otherwise. And so that's how you would calculate the sample variance and the sample standard deviation. So again, not much of a difference, but that's the reason for the difference. But also understanding, am I doing it for a sample or a population? You have to know which one you're dealing with. And so in this case, since we're talking about her having 1,000 friends and only looking at a small sample of 10 of them, that's a difference than saying she only has 10 friends total, and we're looking at all her friends' ages and working with that, and that would be a population. This is a nice little chart that I like to use when I'm calculating my standard deviation. I'll put this in Blackboard for you to use. I mean, you can print them out, you can save it to your computer, whatever. I'll put a copy of this in there separately. And then what you can do is you could fill your data values in here, okay? You could calculate the deviation for each one, square each one of those, take the sum of that column, okay? It's all the steps we did just in the previous example. And then once we get that number, what we're going to do is we're going to divide by, if we're doing it for sample, and this is all set up as a sample, we'll divide that sum by n minus 1, and that'll give us the sample variance. Then we take the square root of that whole thing, and that'll give us the sample standard deviation. So by putting it in this table, listing your data values here, calculate the mean, subtract the mean off of each data value, which is really just calculating the deviation for each particular data value. The problem is when you add all those up, the sum of all those in that column should equal 0. So that doesn't really do a whole lot for us. So we square it, okay? Square each one of these values, here, 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 okay? This column now should be all positive. Add all those values up. Divide by n minus 1, your variance, square root to really to undo that square overall in our calculation and get the standard deviation. So here's another example. We're going to use a sample. So we look at Verizon data speeds. So, Verizon has millions of customers. Let's just look at 5 of them, okay? So we look at 5 different customers' data speeds at a particular location, and we found out that these were the 5 different data speeds for those Verizon customers. And so this is a sample, obviously. There's more than 5 customers for Verizon. And so we could figure out, well, what's the average data speed? And we can calculate the mean. So we add all those up and divide by 5, and we would get a mean of 30.7. And that would be great to know, okay, the average speed for these customers was 30.7. None of the customers actually had a speed of 30.7. Some of them had less than that, some of them had more than that. Okay, so they all deviated away from that mean to some extent. So if we look at each individual data value's deviation, so let's list all the data values here, okay? And let's look at each one's individual deviation from the mean, okay? So subtract the mean off of each one of these numbers. And so the first deviation is 7.8, the next one's 24.9, the next one's negative 8.3, etc. And so you look at all those, and that's all well and good. That's each individual data value's deviation. But if you were to add those all up, you're going to get something really, really close to 0. And sometimes you don't get exactly 0 there because, these might be slightly estimated. And so what we're going to do is then square each one of those. So if I square 7.8 and I square 24.9, I square negative 8.3, I'm going to get this column here. All right, those should all be positive, and you see that they are. That was the whole reason for the squaring process. If we add that column up, we get 1083.06. So what I want to do is I want to calculate the variance. Okay? If I were to calculate the variance, I should take that 1083, which is the sum of all the deviations squared, and I'll divide it by n minus 1. In this case, I'm going to divide by 4. If I divide by 4, which is 1 less than the sample size, which is 5, I'm going to get 270.765. That's my variance. Then I'm going to get the standard deviation by taking the square root of that 270. And I'm going to get 16.45. Now, again, what does this tell me? This is the important number. What does this tell me? What this tells me is that the data speeds in this data set are varying away from the mean, which was 30.7, at a rate of 16.45, in this case, megabits per second. Okay? So it's a pretty big variation relative to the numbers we're looking at. Now, how could that be useful? Well, you could say, all right, I'm a Verizon customer. And then Verizon tells me my average data speed I'll get when I'm using my cell phone is 30.7. And that's a pretty good data speed, I assume. I don't really know a whole lot about data speeds, but let's say it's a pretty good data speed. I mean, okay, if that's your average data speed, I'll like that, okay? And it may be better than the competition, right? But then they go, okay, also, our data speeds vary at a rate of 16.45. Oh, okay, well, what does that mean? Well, if it's varying at a rate of 16.45, it means if I look at my mean, which is 30.7, it could vary away from that mean at a rate of 16.45 in either direction. Now, if it's 16.45 greater than 30.7, great, I'm getting faster speeds. But it could also be less than that, which is taking me down to about like 14 megabits per second, which is not fast at all. And I can go, well, yeah, you might have a good average data speed, but your variation is far too high. I'm going to get too much erratic service from your data speed in this particular situation. So maybe I'll go with a different company who maybe has a slightly lower average data speed. Maybe T-Mobile's average speed is, 27 megabits per second. So it's less. But their variation is only a standard deviation of 2 megabits per second. So even though the average is less, I know I'm going to get closer to that in most cases than something that has a bigger variation. And so that's how the standard deviation will work for you. It tells you how all these data speeds are varying in relation to that mean. So in talking more about this standard deviation and talking about how our data values vary for the mean, typical value that statisticians look at is a value of 2 standard deviations away from the mean, which means 2 times the standard deviation. And what statisticians consider is that anything in that range, bigger or smaller than 2 standard deviations from the mean, would be considered a normal or relatively usual value. So most of our data values should kind of fit into that range. And anything that sits outside of that range, okay, is considered to be unusual, right? And this is what we call a sort of a rule of thumb. It's not like a hard rule we go by, because different data sets could, break this rule. But generally, what we say is that most data values should sit in a 2 standard deviation window away from the mean. So if the mean sits sort of right here in the middle, and we take 2 times the standard deviation and subtract it off the mean and go this distance, and 2 times the standard deviation and add it to the mean and go this distance, we get this interval here. And most of our data values should fall into this interval. In this particular example, the mean was 41.5, the standard deviation was 2.97. So if we do 2 times 2.97, okay, which we're going to get something roughly like 5 point something, close to 6, okay, and add it to the mean and subtract it off the mean, we're going to get this range, okay? We're going to get this range of 35.56 and 47.44. This 2 standard deviation range is considered to be the usual range. Most of our data values should sit into that window. And if you look at all these ages, look, they all sit inside that window. They're all relatively close to each other, okay? But anything outside that window, let's say there was an age of, I don't know, someone was 49, right? Anything outside that window, this would be considered an unusual range of values, an unusual age relative to the data set itself. And so we start to look more and more about how can this standard deviation give us additional information about how our data values relate to one another. How do they vary from the mean? One thing you're going to see us doing throughout the semester is we're going to be comparing different data sets, okay? So data values from different sets. And sometimes that can be very difficult to do, mainly because they might not have any relationship with one another. If we're talking about, say, Jasmine's friends versus my friends, they might have different means, they might have different variations, different standard deviations, in which case you can't necessarily compare them directly to each other. Or let's say you're comparing 2 things that are completely different units of measurement. You're talking about ages of, say, basketball players versus weights of swimmers. Okay? Well, ages and weights, those numbers mean nothing compared to one another. So when we're looking at sort of the variation between them, we would like to try and convert them possibly to what we call a standard scale. And if we can convert different data sets, values, to a different standard scale, so that all the means basically can be related to one another and all the standard deviations can be related to one another, then we can do a really good job at comparing different data sets, whether they're comparable directly or not, right? This standard scale allows everything to be compared. And the way we do that is with something called a Z-score. And so Z-score is going to play a big role moving forward. We're only going to introduce it right now, but it's going to play a big role moving forward. And so what it does is it converts every mean to a value of 0 as, say, like a starting point, a middle value, and every standard deviation to be 1 unit. okay? So in one problem, your standard deviation might be 5. In another problem, your standard deviation might be a variation of 3, but it's going to convert all of them to 1 unit, and that'll allow us to do this comparison. And so the way we do that is through this fairly simple formula. A z-score can be calculated by taking a particular value we're trying to turn into a z-score, subtract the mean, and then divide that by the standard deviation. Okay? Whether it's for a population or sample, we still use z either way. We don't use a different symbol there. Here, the calculation just used the population symbols for mean and for standard deviation. Here, this was the sample mean, sample standard deviation. But x represents the value you're trying to turn into a z-score. And what this z-score will tell us is how far a given value is away from the mean in terms of the standard deviation. So how many standard deviations away from the mean is a particular value? So if I took a data value, let's go back to those ages that we just talked about. Let's say we had an age of, 45. And I want to turn 45 into a z-score. Whatever z-score I get, that'll tell me how many standard deviations. Remember, the standard deviation was 2.97, right? How many of these away from the mean, which was 41.5, is 45? So if I did that real quick, I could say, all right, well, 45 minus 41.5, 41.5 over 2.97, okay? And I know it's hard to say, I don't have much room here to work with, but we'll get done, okay? So 45 minus 41.5 is 3.5. Divided by 2.97, I get a z-score of, let's say, 1.18. So that tells me that 45 is 1.18 of these standard deviations away from the mean, which is 41.5. And so this is going to allow us really to do a lot of work within this semester of comparing data sets. Here's an example, okay? So you have two students, John and Allie. They're from totally different high schools. We wanted to find out who had the highest GPA compared to their school, okay? You know, you can't just look at the GPAs directly and say, all right, let's look at the GPA and give the answer. So you have to compare them to the individual school. So some schools they calculate GPAs differently. So in this case, John's GPA is calculated using a more standard scale. So a 4.0 scale is what normal GPA would be calculated out of. And so his GPA is 2.85. Allie is calculated on a 100-point scale, okay? And her GPA is 77. You might go, okay, just looking at those two numbers, Allie's got the higher GPA, right? But no, that's not necessarily accurate. Whose GPA is highest relative to their GPA scale at their school? Well, the average GPA for John's school is 3, and the standard deviation is 7, okay? Allie's average GPA is an 80, and the standard deviation is 10. So if I was to find the z-score for John and Allie, John's score is 2.85 as GPA. I'm trying to turn that into a z-score. I get negative 0.21, sorry. And Allie, her z-score is negative 0.3. So whose GPA is higher relative to their school? Well, remember, the mean sits right in the middle. Z-scores turn the mean into 0. So John is right here at negative 0.21, and Allie is right here at negative 0.3. So John's is closer to the middle, okay? Closer to the mean of overall than Allie's is. And John has a bigger GPA than Allie does relative to the two of them. So while, you may look at just raw numbers and say Allie has the higher GPA, in actuality, when you convert them to just a standard scale to compare them, John has the higher GPA in comparable to his school versus Allie's comparable to her school.